Alright, hello there. We're going to be addressing in this brief video some derivations of the SHM equations that you'll see in Module 10, and this info may be helpful to you on the test, writing the equations down on the note card and whatnot. So, without further ado, let's get into it. I'm including this summary at the beginning of the video because throughout the rest of the video I'm going to go through my work and show how I got to these equations. And I understand that not everyone has the time or feels like watching me do that. So I've created a nice little slide here, sums it all up. You can take note of all these equations, put them down on your index card. So for our spring equation, we have the spring constant. You know, the default equation is, you have t equals or whatever. You're solving for the period. And this one, I rearranged it, solve for k, and solve for m. Okay, so you can take note of these, write them down. Saves you some time on the test. I mean, you should be able to know how to do this, but I conveniently did it for you. And down here we have energy, so your base equation is going to be Ke plus Pe equals Te, and then I went in, substituted all the variables and stuff, and so we solve for amplitude, delta x, the spring constant, and then the mass. And then finally, for our pendulum equation, I found the length of the pendulum, and then the acceleration due to gravity, if you ever need to find that, which you probably won't, but just in case. So with that in mind, go ahead, pause the video here or whatever, and write down all of this. The other equations should be given for you. Notice that I didn't solve for V in the energy equation. Where's V? Because that is given to you on your sheet. So go ahead and pause the video, take a few seconds, and then when you're done, you can go ahead and close it out, or you can continue watching and I'll show my work. Alright, welcome back. Let's begin. So here's a sheet in which you're given velocity, base equations, and all that. And so we're going to be taking everything from 2 all the way down to 4 here, and pretty much solving for each letter, except the ones that are given. So we don't need to solve for T, but we can solve for L or G, as you saw in the previous slide. So let's get into it. The equations that will be analyzed, we got spring, energy conservation, and then the pendulum. So let's start with spring. Take the base spring equation, can be found on the handout, section number 2. Period equals 2 pi times the square root of the mass times divided by the spring constant. And the derivation for this gets even deeper that you can find in the book and stuff. So we're going to solve for the spring constant K first. And so to do that, we take our base equation. Next we're going to square both sides. D squared equals 4 pi squared times the mass divided by the spring constant. That eliminated the radical. It allows us to freely move around the variables and stuff. So now that we can freely move around the variables, we're going to get rid of all the fractions here. Get k over to one side. So multiply both sides by k, getting rid of the denominator here. And to isolate k by itself, we divide both sides by t squared here. So we end up with k equals 4 pi squared times m divided by t squared. And now for these spring equations, I'm going to run through and do a unit check on our final answer, just to make sure that everything looks good in the end. So we have m is mass in kilograms, t is period in seconds, 4 and pi are unitless. So we end up with spring constant is equal to m for kilograms, and then divided by seconds squared because we have t is equal to seconds, and then we square that. kilograms divided by seconds squared is actually equal to a Newton meter. And remember, Newton divided by meter is our unit for K here. And so I can prove that because we take Newton divided by meter, kilogram times meter, divided by second squared, divided by meter. The meters cancel, and we end up with kilograms divided by seconds squared. Okay, next equation here, we're going to take our base with the period, and now we're going to solve for the mass. So first step, take the square of both sides again, get rid of that radical. Next, multiply both sides by k again, get rid of this nasty fraction here. We can have all our variables in a straight line. And then to get rid of m, we just divide both sides by by 4 pi squared, so that we isolate m here. And then I just swap the sides, because you're allowed to do that. And so we end up with t squared times k divided by 4 pi squared. Now our unit check, this is the equation we came up with here from the previous slide. The period is equal to t, and that's in seconds. K is a spring constant, which is in Newton, Newton divided by meter, which is also kilograms per second squared, as we proved a few minutes ago. So plugging that in, we have second squared for the t, comes down to there, and then the k is kilograms divided by second squared, goes over there. And now if we combine them into one fraction, because this is essentially second squared divided by 1 here, remember? So we can do this legally, and then the second squared cancel, and we end up with a mass in kilograms, which is what we want. And that looks good. Okay, next equation, we're going to take our base energy equation, simplify it so that we can use it and rearrange some stuff here. So we start with TE equals PE plus KE. We substitute our givens, which can be found on the sheet that I referred to earlier in the video. And now we factor out the 1/2 because it appears in each term. So we're allowed to get rid of that, cancel it out. And that's the end of the equation there. So this is our final version. Now we take that and we plug it into here. And now we're going to solve for the amplitude, which is A. So we take our base equation. Next step is to divide both sides by k. And since the k appears here, it cancels out with that. And then we end up with mv squared divided by k being added to it. Now we take the square root of both sides. And you may be wondering, well, Eli, why don't you just do square root of x squared as one term, and then have the plus, and then the space, square root of this? And well, my answer is you're not allowed to do that. That plus right there is preventing me from separating the two terms. So I have to leave my answer like this, which is, looks a bit nasty, but it's physics. It doesn't look pretty, huh? Okay. Now we have delta x here. So our base equation, we're going to isolate delta x slowly by subtracting mv squared from both sides. Then we divide both sides by k. And we have delta x off on the side by itself here. Again, we can cancel out the k there, and then this just ends up being mv squared divided by k. Now to get rid of that square to the second power sign, take the square root again, and we end up with this big nasty equation. And that is our proof. Next one is the spring constant, our k right here. So we have our base equation. We subtract the k times delta x squared from both sides. Next, we're going to factor out the k from the left side because it appears twice. in each term, so we're allowed to do that. Next we divide both sides by this big chunk of a beast, and we end up with k is equal to mv squared divided by amplitude squared minus displacement squared. And that is our final answer. Next step is to solve for mass. So we have our base equation. We're going to want to isolate the mv squared term here so that we can then isolate the m. So to do that, subtract k times delta x squared from both sides. Now we have our mv squared over here. And from here the step is fairly simple. You should be able to do it in your head. Divide both sides by v squared. And then there's a final simplification step here because k appears twice. And so what we can do is factor that out so that we don't have to have someone go in and do k a squared minus k delta x squared and all that work now. They can just do a squared minus delta x squared times k squared. Sorry, times k. And divide that by velocity squared, and then they have the mass. And that is it for the energy. We'll move on to pendulum now. Okay, we got our base pendulum and simple harmonic motion equation. This can be found in the handout, section number 4. And if we notice, this is extremely similar to the base spring equation in SHM, except we just have an L and a G to deal with. So we can substitute and pretty much exchange some terms here. We swap out the M in the spring equation with our L for pendulum, the length of the pendulum, and the K, the spring constant, in exchange for the acceleration due to gravity. So observe. We can rearrange. So what I've done here is I've taken our other equation where we had M in place of L divided by K. That's a garbage K, but you get the point. And so what I've done is I've swapped the terms, and it comes out exactly the same. You solve for G, you end up with 4 pi squared times L divided by T squared. And so you can run through this, and it checks out. Same thing for solving for the length of a pendulum. Solving for L. So we just follow the exact same steps that we did earlier on, and it comes out evenly. It's like you're just doing a little swap-a-doodle-doo there. But I went through and proved it anyway, just in case you guys are suspicious. Thank you for watching. I hope this was a bit helpful. You're able to enjoy it and follow. If you have any questions, don't hesitate to ask or point out a flaw in my math or something. I wish you the best.